Okay, so we are going to be talking about momentum and impulse in these set of notes. Again, I would like for you all to copy down the notes as they are. Please feel free to add any additional notes of your own as I walk through these notes and talk through my own explanations. I encourage you all to always do that as we work through these notes. Okay, so our topic for today, as I just said, is on momentum and impulse. The objective is to be able to describe and calculate the momentum and impulse of an object. So your essential question that kind of aligns with that objective is, how can I use momentum and impulse to describe an object's motion? So at the end of taking notes right now, once you finish your notes, you should read through your notes again and then try to answer this essential question in your summary at the bottom of your notes. And please remember to include your summary. It's very important to learning, be able to summarize what you learned. Okay, so let's talk about momentum first. So when we talk about momentum, you all have probably heard the momentum in another context before, but for physics, momentum is described as, I don't know why this is not working. Give me 1 second. So for physics, momentum, and I just pulled up the wrong tool. Let me get my highlighter out. All right, there we go. Momentum is described as the quantity of an object's motion. So key word here is quantity. So quantity means how much, right? Describes how much of something you have. So what momentum is really telling us is how much motion an object has. So we use a couple things when we're talking about momentum. Again, when we talk about the difference between vectors and scalars in physics, momentum is a vector, meaning it tells us how much of something, right? How much momentum an object has and the direction of its motion. The variable that we use for momentum is a lowercase p. Again, I don't really know why. I'm assuming it's because lowercase m was already taken by mass. So your equation for momentum, and I will get out my highlighter here. Your new equation for momentum is P equals mv. All right, so this is another nice 3-variable equation. And just so we are clear, remember, P is momentum. M is going to be the mass of the object. And V, lowercase v, remember, stands for the velocity of the object. All right. Because we are multiplying mass and velocity, the unit of measurement for momentum is kilogram times meters per second. You'll notice kilogram is our unit of measurement for mass. Meters per second is our unit of measurement for velocity. That makes sense because we are multiplying both of those together to get momentum. So our unit for momentum is kilogram meters per second. All right. So a main takeaway here. Momentum, since it is calculated using a mass, momentum simply also describes mass in motion, right? An object has to be in motion to have a velocity, and an object has to have a mass. So momentum is simply mass in motion. All right, so let's work through an example here. I'm going to zoom in. All right, so say we have this example here. A car with a mass of 1,000 kilograms travels with a velocity of positive 2 meters per second. What is the car's momentum? All right, so again, we are going to follow our 4 steps to solving a physics word problem to solve this problem. So the first thing we need to do is draw a picture. Now, I've already drawn a picture for you all, but again, please make sure you are following all 4 steps whenever you are solving a picture, or excuse me, whenever you are solving a word problem. All right, it really helps to draw these pictures out so you can get a visual. All right, so we know that the car's mass, I'm going to pick different colors here. All right, so we know from the problem that the mass is 1,000 kilograms. So I'm going to move on to step number 2 and write M is equal to 1,000 kilograms. All right. We also know the velocity. The velocity, and I'm going to pick a different color. All right, so our velocity is positive 2 meters per second. Again, remember, positive direction is moving to the right according to our XY coordinate plane. So our velocity is positive 2 meters per second. All right, so what we don't know, this is again what the problem is asking for. So if you ever get stuck on what you don't know, just look at the question. It asks, what is the car's momentum? So I'm going to write P, lowercase p for momentum, is equal to question mark. Right? So again, this is a really nice 3-variable equation here. So we can actually use our triangle trick to solve for momentum. Again, when we are setting up our triangle trick, the numbers that are being, or excuse me, the variables that are being multiplied together are going to go on the bottom of the triangle. We know that when 2 variables are next to each other, it means they're being multiplied together. Once they're multiplied together, they equal the variable that is put on top. All right, so again, we are using P equals MV to set up our triangle here. P is the number on top. M times V, which are next to each other on the bottom, we know that that is multiplication there. So we know that M times V is multiplication. All right, so and I'm going to quickly erase this to make a little bit more room. All right, so we are solving for momentum here. So when we are doing the triangle trick, you are going to cover up which variable you do not know. So I'm going to write this in transparent, but again, you cover up with your finger the variable that you don't know. So I don't know what momentum is. So I'm going to write P equals. And then once I cover it up with that triangle, or it's covered it up with my finger on my triangle, I see, oh, okay, P is equal to MV. Now I've got my equation ready to go. That's step number 3 to solving a physics word problem. Once I've got my equation ready to go, I am good to plug in. So the number that I am plugging in for M right here is going to be 1,000. And I put a dot to indicate multiplication. The number that I am plugging in for V is going to be positive 2. And I can multiply those together. And 1,000 times positive 2 is going to be positive 2,000 kilograms meters per second. And that is my final answer. That is my final answer for calculating the momentum of an object. All right, so now that we've gone over momentum, we can talk a little bit more about impulse. So we use impulse for a variety of things. Impulse is really helpful when we're talking about collisions of objects, when we're talking about an object's change in motion. We can talk about all different things in terms of impulse. So impulse is really helpful for us as physicists, but also for engineers, for a variety of different applications. So the definition of impulse is simply the change in an object's momentum. So remember, we know a symbol that indicates change. We know that the Greek letter delta, this triangle, means change. So whenever we see that triangle, we are looking for the change in that specific thing. So if you see a triangle next to a P, that means we're looking for the change in momentum. When you see a triangle next to a V, we're looking for the change in velocity. So again, that triangle is really helpful for us when we're talking about the changes in various things in physics, right? So impulse is also a vector. It cares about how much impulse there is, as well as the direction of the impulse. The variable that we use for impulse is a capital letter J. Again, I am not really sure why, aside from the capital letter I was already taken. So we are using a capital letter J to calculate impulse. There are actually two ways that you can calculate an object's impulse. So the first equation that you all will see is that impulse is equal to our change in momentum. That completely makes sense because impulse is literally defined as the change in an object's momentum. So how we calculate the change in momentum, that is the rest of this equation here. So momentum can be changed by changing an object's velocity, right? We can't really change an object's mass, but we can certainly change an object's velocity. So I will make a note that right here in these parentheses, this is a change in velocity. Y'all are familiar with this. Final velocity minus initial velocity. So that is our change in velocity. There we go. All right, another equation that we can actually use to calculate impulse is J equals F times T. So you should be familiar with these variables. F is the force acting on that object, and T is the amount of time it takes for that force to act on the object. So F times T is equal to impulse as well. And this makes sense again because to change a mass in motion or to change an object's momentum, a force is required to change that momentum. It's required over a certain period of time, right? Think back to Newton's first law of motion. An object in motion will stay in motion. It will not change its motion unless it's acted upon by a force. So we do need a force to have impulse. The unit of measurement for impulse is newtons times seconds. Again, this makes sense based off of how we are calculating impulse. Force is measured in newtons. Time is measured in seconds. We are multiplying force times time to get impulse. So that's how we get the unit of measurement for impulse, is the unit of measurement of force, which is newtons, times the unit of measurement for time, which is seconds. All right, so I've included two examples here for how we might calculate an object's impulse. So let's use this example first. I'm going to zoom out a tad. All right, so in this example, a person with a mass of 73 kilograms begins from rest and speeds up to positive 5 meters per second. What is this person's impulse? Again, we are going to use the 4 steps to solving a physics word problem to solve this problem. So the first step is to draw a picture. So our picture says this person has a mass of 73 kilograms. They start from rest. I'm going to add that. Start from rest. And they move to a velocity of positive 5 meters per second. All All right, so let's make a list of what we know and what we don't know. All right, so first thing we see, mass of 73 kilograms. So I can write in my column, M equals 73 kilograms. All right. They begin from rest. Now that should indicate something about that object's motion. Okay, they're starting from rest here, which means that their initial velocity, their starting velocity, so I'm going to write VI for initial velocity, is 0 meters per second. All right. Then they speed up to positive 5 meters per second. So they are starting from rest and then they speed up. That tells us that the final velocity, which I will write VF, is equal to positive 5 meters per second, right? So again, we don't know the person's impulse. And I just highlighted that with the wrong color. We do not know the person's impulse. So we want to find that out. So I'm going to write J equals question mark. Right? So now we have to set up our equation. Thankfully, we have a pretty easy equation, but we have two options here. So we need to think about what we are given and decide on the equation that makes sense to solve with. So we are not given anything about force or time here. So it doesn't really make sense to solve for impulse if we have no information here about that person's force or time. So let's use this other equation here, that impulse is equal to momentum, or excuse me, is equal to the change in momentum, which is the mass times the change in velocity. So we have that equation ready to go. All right, so now that we've got that ready, we can start plugging those values in. So for mass, I'm going to plug in 73 kilograms. For our final velocity, right here, I'm going to plug in positive 5 meters per second minus the initial velocity, which we know is 0. Now that we've got everything in, again, make sure you are following PEMDAS. So if we follow PEMDAS, we are going to have, let me just write this again, 73 times positive 5 minus 0. So that is going to be equal to positive 5. 73 times positive 5. You can plug that in your calculators if you want, is equal to an impulse of positive 365. And again, remember our new units that we learned, newtons seconds. All right, so that is one way we could calculate impulse. Another scenario we might have is a soccer ball travels with a velocity of positive 5 meters per second. A force of negative 10 newtons is applied within 0.1 seconds to change the soccer ball's velocity to negative 3 meters per second. What is the impulse of the soccer ball? All right, so here's our scenario here again, and this is why it's important to draw things out, because we do have a change in direction, change in velocity, and a change in direction. So we have our initial soccer ball, which is traveling at positive 5 meters per second. And then fast forward to a new scene, and that soccer ball has changed directions. There has been a force applied to it to change its direction to the opposite direction. So now it is traveling back to the left. All right, so let's work through this problem, figure out what we are given first. All right, so soccer ball travels with a velocity of positive 5 meters per second. So I'm going to write, okay, here's our velocity. All right, and I will put that in here. We have our initial velocity, which would be positive 5 meters per second, okay? And then we have a force of negative 10 newtons, all right? So we've got a new variable here, force. So I'm going to write capital F for force, negative 10 newtons, all right? Is applied within 0.1 seconds, all right? So we know seconds measures time, so we can indicate, okay, here is our time. So I'm going to write T is equal to 0.1 seconds, right? To change the soccer ball's velocity to negative 3 meters per second, right? So its final velocity is going to be negative 3 meters per second. All right, so again, we are solving for the impulse of the soccer ball. So we don't know capital J for impulse, okay? All right, so we've got our list of things we know and list of things we don't know. Let's look back at our equations here. So we've got two options here. We could use m times vf minus vi or f times t. So let's look at what we have here. Well, we've got vi and vf, but the problem, unfortunately, did not give us anything about the mass. So we do need the mass to solve for using the change in momentum equation. So unfortunately, we cannot use the first equation because the problem did not give us the mass of the soccer ball. However, we do have force and time. So we can look back up at this equation and say, oh, okay, we do have enough information to use our second equation. So the second equation, as a reminder, is J is equal to FT. And again, if you want to use your triangle trick, F and T are being multiplied together. To equal J. So again, if you, whatever you are solving for, cover that up with your finger and you should get the equation set up the way you want it. So again, if we cover up J, we know that we are multiplying F times T to equal J. All right, so now we've got everything set up. Let's start plugging things in here. So for F here, I'm going to plug in negative 10, and I'm just putting parentheses around it so I don't lose track of my negative signs. Negative 10 times T, which is 0.1 seconds. Again, just putting parentheses around here just to keep track of those numbers. All right. And once I multiply those together, and you can follow along as we do that, you should get that the impulse is negative 1 Newton second. So that is another way we can solve for an object's impulse. All right, so I hope that this was helpful for you all. I know that was a lot of material that we covered and a lot of practice problems, but I hope this helps clear up some information about momentum and impulse. I look forward to discussing this with you all in class.